Hello everyone. In this video, we are going to explain what AXI4-Lite is, why it matters in system-on-chip design, and how an AXI4-Lite write command works. After that, we will design a custom AXI4-Lite slave block from scratch in Verilog. The IP block we will design in this video will be used later in a larger project where we run a fast Fourier transform in real time using an analog to digital converter. In this lesson, you will learn how to make a Verilog module receive and process AXI4-Lite write commands from a processor. Once you understand this, you can use the same idea to make many different custom IP blocks controlled by software. Alright, so let's get started. In an FPGA-based system-on-chip design, the system is often organized into two major sections. The first is the processing system, which contains the softcore processor that runs the software and controls the system. The second is the programmable logic, which controls the IP blocks and the custom RTL used by the processor. The processor needs a way to communicate with IP blocks and custom pieces of RTL. AXI4-Lite provides a standardized protocol that allows the processor to read and write to registers inside IP blocks and custom pieces of RTL. By reading and writing to registers, the processor can configure hardware settings, start operations, read results, check status flags, reset hardware blocks, enable interrupts, and control how different IP blocks behave. In other words, AXI4-Lite is a communication protocol that allows a processor to read and write values from a slave device. This means that the processor only ever uses AXI4-Lite to do two things. The first is writing a value into a register. For example, the processor can write value X into register Y. The second is reading a value from a register. For example, the processor can read value X from register Y. For custom Verilog IP, this means that the IP block must know how to store data during write commands and return data during read commands. In this lesson, we are only focusing on write commands. Read commands will be covered in the next lesson. When the processor issues an AXI4-Lite write command, data is sent from the processor to a register inside of the custom IP block. The write transaction uses three phases: write address phase, write data phase, and write response phase. The table below shows which signals are used in each phase and whether each signal is driven by the processor or IP block. When the processor executes an AXI4-Lite write command to a custom Verilog module, the Verilog module uses the pink signals as inputs and the green signals as outputs. It does so by using the following rules. The following animation shows exactly what happens during an AXI4-Lite write command. At time t0, the IP block already has AW ready high, meaning it is ready to accept a write address. At time t1, the processor drives AW address, AW prot, and AW valid. AW address contains the register address the processor wants to write to. AW prot is set to 0 for normal writes, and AW valid tells the IP block that the processor has sent a valid write address. At time t2, AW valid and AW ready are both high at the clock edge, so the IP block saves AW address. After this point, AW address and AW prot are no longer relevant to this write transaction. The processor lowers AW valid, and the IP block lowers AW ready. The IP block also raises W ready. At time t3, the processor drives W data, W strobe, and W valid. W data contains the data that the processor will write. W strobe indicates which bytes of W data are valid. For a full 32-bit byte, W strobe is usually F. W valid tells the IP block that the processor has sent valid write data. At time t4, W valid and W ready are both high at the clock edge, so the IP block saves W data and W strobe. After this point, W data and W strobe are no longer relevant to this write transaction. The processor lowers W valid and the IP block lowers W ready. At time t5, the IP block has already saved the write address and the write data. The saved address tells the IP block which internal register should be written into. The saved data tells the IP block what value should be stored in that register. Using both pieces of information, the IP block writes the saved data into the selected register. At time t6, the IP block drives bresp and bvalid. Bresp is set to 0, meaning that the write is finished. The IP block uses bvalid to tell the processor that the write operation is finished. At this point, the IP block is saying that the register write has finished and a response is ready. At time t7, the processor drives BReady high. BReady tells the IP block that the processor is ready to acknowledge that the write operation is finished. bvalid stays high because the completion has not been acknowledged yet. At time t8, bvalid and BReady are both high at the clock edge, so the processor acknowledges that the write operation is finished. The full AXI4-Lite transaction is now complete. After this point, bvalid and BReady can go low. bresp is no longer relevant to this write transaction, and the IP block resets back to its initial state. As an example, we will design a Verilog module that receives a write command from the processor and generates a start pulse when the correct data is written to the correct address. The slave we will design will generate a 1 clock cycle long start pulse every time it receives a valid AXI4-Lite write command to the register specified by the start reg address parameter, with bit 0 of the written data set to 1. The start reg address value is configurable, allowing the start register address to be changed as needed. To make this IP block, we must write a custom module in Verilog and then package it as a reusable Vivado IP block. This piece of IP will be used in a future video where we run a fast Fourier transform in real time. Alright, so this here is the Verilog code used to implement the custom AXI4-Lite IP block. On lines 1 through 42, the module parameters and ports are declared. The parameters define the AXI address width, the AXI data width, and the start register address. The start register address is the address that the processor must write to in order to generate the start pulse. On lines 8 and 9, we declare the clock and reset. On lines 11 to 26, we declare the AXI4-Lite write channels. These are the signals used by the processor to send a write command into the IP block. On lines 28 through 38, we declare the AXI4-Lite read channels. This video is focused on the write commands, so the read side is not the main topic here. However, these signals are included so that Vivado packages the module as a complete AXI4-Lite slave interface. This allows the block to connect cleanly to the MicroBlaze AXI interconnect without strange manual connections. On line 41, we declare the custom output signal start pulse. This is the signal that will go high for 1 clock cycle when the processor writes the correct value to the correct address. On lines 48 to 52, we define the 5 states. Each state matches one of the 5 AXI4-Lite write rules explained earlier. On lines 54 to 59, we define the internal registers used by the state machine. The register on line 54 stores the current state. The registers on lines 57 to 59 store the write address, write data, and byte enable values received from the processor. On lines 61 to 75, we implement the reset behavior for the write logic. When reset is active, the finite state machine returns to the initial state, the AXI response signals are cleared, the saved values are cleared, and the start pulse is forced to low. The remaining logic implements the 5 rules. On lines 84 to 97, we implement Rule 1. This is the initial condition state. The IP block raises AW ready, keeps W ready low, clears bresp and bvalid, clears the saved write information, and then moves on to the address save state. On lines 104 to 113, we implement Rule 2. When AW valid and AW ready are both high, the IP block saves AW address, lowers AW ready, raises W ready, and moves to the data save state. On lines 120 to 129, we implement Rule 3. When W valid and W ready are both high, the IP block saves W data and W strobe, lowers W ready, and moves to the write complete state. On lines 136 to 148, we implement Rule 4. This is where the IP block uses the saved address and saved data to complete the internal write action. If the saved address equals start register address and bit 0 of the saved data is 1, then start pulse is raised. The module also drives bresp to 0 and raises bvalid to indicate that the write response is ready. On lines 157 to 166, we implement Rule 5. In this state, start pulse is lowered so that it only lasts one clock cycle. Then, when bvalid and bready are both high, the module lowers bvalid and returns to the initial state. Finally, on lines 176 to 197, we implement a simple placeholder for the read logic. Since this video is not about read commands, this section simply accepts a read request and returns 0. To prove that this IP block actually works, we need to put it inside of a real hardware project. That way, the MicroBlaze processor can send AXI4-Lite write commands to it, and we can use the ILA to see whether the start pulse gets generated when the correct value is written. Before we can do that, we must first make 3 folders. We need a folder for the exported hardware, which will initially be empty. We need a folder for the IP file, which will initially contain the Verilog file for our IP. And lastly, we need a folder for the workspace that Vitis will use, which will initially be empty. After you have opened Vivado, create a new block design. Then add in the MicroBlaze processor and the clocking wizard. Then remove the extra ports from the clocking wizard. Our custom Verilog IP will not automatically appear in the IP manager. To make it show up, we first need to package the Verilog module that is stored in the IP folder. Now that it has been packaged, we can add it. Then, run block and connection automation. Make sure to set local memory to 64 kilobytes. Then add in the constraint file. In the constraint file, we only have the 100 MHz clock and an output for the start pulse. We must rename the ports in the block design to match the names in the constraint file. We must also delete the reset pin and hardwire it to a constant value of 1. This removes the need for a separate reset port and ensures that the reset is never used. In simple terms, this is our way of disabling the reset feature. Next, we must set the address of our custom IP block to 57000000. We must do it in both the address editor and the block diagram. We must then add in the internal logic analyzer and connect it so that the start pulse is monitored. Then, you must generate an HDL wrapper and generate the bit stream. After the bit stream is generated, click OK. Then export the hardware. Make sure to select the folder that we made for it at the start. This was the folder named EH. Then open the hardware manager and program the device. Then set the ILA to trigger when the start pulse has a value of 1. Then launch the Vitis IDE. Make sure to launch the Vitis IDE in the folder that we made for it. This folder was named WS. Then, create an application project. Select the exported hardware file. Give your project a name. And then finally make a blank project. Then make a new source file and paste in the code. Then click the hammer to build the design. After the design has finished building, click Run Configurations, then click System Project Debug, then click Target Setup and uncheck Program FPGA, then click Apply and then Run. After it is finished running, get Vivado and Vitis side by side. Then arm the ILA and run the Vitis code. You will see that when the code runs, the start pulse gets generated. This is expected because the code is causing the processor to write the right data into the right address. If we arm the ILA and run the code again, the same thing will happen. Then, if we change the code to write the wrong data and try it again after rebuilding, we will see that the start pulse is never generated. This is expected since the IP was designed only to make the start pulse when the least significant bit of the right data was 1. Then, if we change the code to write the right data and try again after rebuilding, we will see that the start pulse is generated. Alright, you have now been taught everything you need to know to design custom pieces of IP that can accept AXI4-Lite write commands. In the next video, you will be shown how to do the same thing, but for read commands. If you enjoyed this video and want to learn more, then consider buying the book that I used to make these lessons. Purchasing the book also gives you access to the Discord community and additional materials that are not shared publicly, making it a strong investment if you are serious about mastering digital design. It also supports the channel and helps me keep making high-quality content. The link to the book is in the video description. That's all for now. Thanks for watching, and I'll see you in the next one.